Hello, my name is Grenville Croll. I'm the author of the paper entitled BiEntropy, TriEntropy and Primality. Thank you for your interest in my work. 7 years ago I developed the BiEntropy function to determine the relative order and disorder of arbitrary binary strings. For example, the 8-bit binary string 01010101 is ordered as its bits are repetitive with a periodicity of 2, whereas 10011101 is disordered as there is no discernible pattern. BiEntropy is a hierarchical weighted average of the Shannon Entropies of the string and all but one of the binary derivatives of the string. Perfectly ordered binary strings have a BiEntropy of 0, and perfectly disordered binary strings have a BiEntropy of 1, with every flavour in between. I successfully tested the BiEntropy algorithm in a number of diverse areas, including assessing the prime constant for disorder and affirming theoretically by two simple corollaries the irrationality of the prime constant. BiEntropy has subsequently been used by others in the fields of cryptography, random number generation and mobile telecommunications. Importantly, it has been re-implemented and retested by the US defense establishment on GitHub and prominently cited in a related US government patent regarding an unclonable integrated circuit device for random number generation. And so 6 years were to pass before I spent an hour colouring in figure 1 of my original paper, or figure 1 of this current paper, to show where the primes less than 256 lay with respect to BiEntropy. It turns out there's a deep relationship between BiEntropy and primality, and I'm sure you'll find the simple result very surprising. I've spent most of my working life using spreadsheets, and so was easily able to test and confirm this initial empirical result more widely using a Monte Carlo simulation on the 32-bit numbers. Since we know that all primes greater than or equal to 5 are of the form 6k plus or minus 1, I was motivated to develop the TriEntropy function using trinary arithmetic, which showed similar results. The theoretical basis behind these results is as surprising as the initial results themselves. I established a simple theory of periodic numbers which proves that the periodic numbers in any base cannot be prime, with two important exceptions, the primes themselves and the Fermat numbers. We are thus able to reorder the number line into quadratic or cubic order based upon BiEntropy, TriEntropy, or the additive combination. We can do this because BiEntropy computes almost exactly the probability of a number being either not prime or prime, based purely upon the proven mathematical properties of its binary derivatives. The error in the quadratic or cubic is Gaussian and tiny, and in fact it's 0 in the limit. The independence and Gaussian nature of the binary derivative, and hence the primes by a simple induction, plus one other necessary property, were proven in two important papers which appeared about 50 and then 25 years ago. Their results have lain almost unused until now. In the discussion of our results, we show that the error between the bientropic prime density and the associated quadratic prime density tends to 0 as x tends to infinity. This implies that the variance of the difference between πx and Lx also tends to 0 as x tends to infinity. This bound on the variance of the difference between πx and Lx is much tighter than the bound on the error between πx and Lx proven by von Koch in 1901 as being an equivalence of the proof of the Riemann hypothesis. Since the primes are Gaussian due to a simple induction on the binary derivative, this implies that the twin primes conjecture is true. The methodology also exposes two absolutely convergent asymptotes for the numbers of Fermat and Bazin primes, which do not appear to have been previously published. So finally, I would like to thank my MDPI editor for her assistance in supervising this paper, the anonymous referees for their comments, and my colleagues at AMPA, PAMPA and Newsbrig for their advice, contributions and support. I thank my wife for her support over many years. Again, thank you for your interest in my work.